So for 80 years after Einstein proposed his general theory of relativity, it was viewed as a theory of gravity. And it's been a very successful theory of gravity. But in recent years, we've learned that general relativity can also describe aspects of non-gravitational physics, including condensed matter. It might even provide insight into mysterious properties of high-temperature superconductors. And it's this remarkable new development that I'd like to tell you about today. So an outline of this talk is as follows. I will start with a brief review of general relativity in black holes, because they'll play a crucial role in this story. I'll then introduce this remarkable gauge gravity duality, which is the main tool which allows us to use general relativity to describe non-gravitational physics. And finally, I'll tell you how we are using general relativity to study superconductivity. So, as you all know, the main idea of general relativity is that since gravity is universal, affecting all objects in exactly the same way, we identify it with something else which is universal, namely the geometry of space, time itself. The main equation in general relativity is Einstein's equation, which relates the curvature of the space-time to the distribution of matter. And general relativity also says that particles moving in the curved space-time follow special curves called geodesics, which are the straightest possible paths in this curved space-time. General relativity has been extremely well tested by now. Let me just give you one example. Of course, an early prediction of general relativity is that light is bent by massive objects. That was, in fact, the main experimental confirmation that Eddington led an expedition to confirm in 1919 during an eclipse of the sun. But at that time, the data was very, very crude. Accuracy was I don't know, in the tens of 30% or so, perhaps. But today, we have much more accurate measurements. And in fact, this bending of light prediction has now been confirmed to 2 parts in 10 to the 5 by bouncing radio waves off the Cassini spacecraft when it was on its way to Saturn, and the spacecraft was on the other side of the sun. Well, the main classical, well, I should say, of course, that the amount that light is bent is determined by how compact the object is. If the object is compact enough, then indeed the light is trapped, and you get the prediction of black holes. The main classical properties of black holes were developed in the 1970s. And one of the most surprising was this uniqueness theorem. It was shown that the only stationary vacuum black hole solution in general relativity is the Kerr solution, which has only 2 free parameters, the mass and angular momentum. John Wheeler described this by saying black holes have no hair, meaning that there's no distinguishing characteristics of the black hole outside the event horizon other than these 2 conserved quantities. This came as a big surprise, of course, because you can form a black hole by collapsing matter with all different multiple moments, but the claim is when it settles down, it will be completely described by just these 2 parameters. Another key parameter in describing a black hole is the surface gravity, often denoted kappa, and this can be viewed as the force at infinity that you have to exert in order to hold a unit mass right near the horizon of a black hole. Of course, locally the force diverges, but there's a redshifting effect, and the force at infinity remains finite in this limit, and that's called the surface gravity. So in 1973, Carter, Bardeen, and Hawking formulated 3 laws of black hole mechanics. The first law, which they call the 0th law, for reasons that will become clear in just a second, states that for a stationary black hole, the surface gravity kappa is constant over the horizon. This is not a surprise for non-rotating black holes, since they're spherically symmetric and everything is constant on the horizon. But the statement is this is also true for rotating black holes, which are distorted and oblate and not uniform. But K nevertheless, the kappa surface gravity nevertheless is constant. They also showed that under small perturbation, the mass, of course, and angular momentum will change a little bit. The area of this horizon will change a little bit. And they showed that they're related by this formula. The change in the mass is the surface gravity divided by 8 pi times Newton's constant times the change in the area, plus another quantity which is called the angular velocity of the horizon, a measure of how rapidly the black hole is rotating. And that multiplies the change in angular momentum. And finally, they showed that the area of the event horizon always increases. And of course, it was immediately noticed that there's a close analogy between these laws of black hole mechanics and the ordinary laws of thermodynamics. If you view kappa as analogous to a temperature and the area of the event horizon as analogous to an entropy, these are indeed the laws of thermodynamics. The temperature of an object is constant in equilibrium. This is the usual first law. dE is T ds, plus some rotation term. And the entropy always increases. But of course, at the time, it was thought this could only be an analogy, because if black holes really had a temperature, they had to radiate. And everybody knew nothing could come out of a black hole. Well, just a year later, everything changed. Hawking studied quantum matter fields coupled to a classical black hole and showed that indeed black holes radiate with essentially a black body spectrum with a temperature that was indeed proportional to the surface gravity. And he found the constant of proportionality. It was Planck's constant divided by 2 pi. So the temperature is h bar over 2 pi times kappa. And from the first law, that shows us that the entropy is 1 over 4 Planck's constant, Newton's constant, times the area of the event horizon. Now, for astrophysical black holes, this temperature is very low and has no astrophysical importance. And the entropy is enormous. In fact, much larger than the entropy of the matter that collapses to form a black hole. I'll come back to that in just a second. But for now, let's move on. And I want to claim, as I said at the beginning, that in addition to describing gravitational phenomena, such as black holes, gravitational waves, etc., general relativity can also describe other fields of physics, including condensed matter. So I'll try to convince you that that's not as crazy as it sounds. And the main tool, as I said, is this gauge-gravity duality. To explain this, I have to say a few words about gauge theory and string theory. So a gauge theory is just a generalization of ordinary electromagnetism in which the U1 gauge symmetry or gauge invariance is replaced by a non-abelian group, for example, SUM. Our standard model of particle physics is based on a gauge theory, in particular quantum chromodynamics. Our theory of the strong interactions has an SU3 gauge symmetry, and these interactions are weak at high energy, but become strong at low energy, causing quark confinement. Gerard de Hooft argued in the 1970s that a 1 over n expansion of an SUN gauge theory would resemble a theory of strings. And he argued for this based on the structure of the perturbation theory when you do this 1 over n expansion. And it took more than 20 years before this idea was made precise. So what's a string theory? String theory is a promising candidate for both a complete quantum theory of gravity and a unified theory of all forces and particles. It's based on the idea that elementary particles are not really point-like, but just excitations of a one-dimensional string. A one-dimensional string traces out a two-dimensional world sheet in space-time, and the basic assumption of string theory is that the interaction between strings is a simple splitting and joining interaction. So you can have one string split up into two, or two strings can combine and form one. And there's a certain coupling which describes the strength of that interaction. Although it's not immediately obvious, it was shown early on that string theory includes gravity, and in fact reduces to general relativity in a certain classical limit. This was first shown by quantizing the string in flat space and finding that there is a massless spin 2 excitation of the string, which looks like a graviton. When you go through the calculations of how those gravitons interact, just assuming the splitting and joining of strings, you find that you reproduce a perturbative expansion of general relativity just on how these gravitons are interacting. But it was later shown that you don't need to resort to perturbation theory. If you put a string in a curved background and try to quantize it, there's inconsistencies unless the background actually solves the Einstein equation, the full non-perturbative Einstein equation. So you get general relativity out of string theory. Well, let's now come to the main point. Gauge gravity duality was first proposed by Maldacena back in 1997. This duality states that under certain boundary conditions, which I'll specify in a moment, string theory, which I just said includes gravity, is completely equivalent to a non-gravitational gauge theory living on the boundary of space at infinity. I mean, at first sight, this seems completely crazy. These theories look totally different. How can they possibly be equivalent? And, well, the key point is that this is a strong weak coupling duality. When string theory is weakly coupled, and we have some intuition for what the theory is like, the gauge theory is strongly coupled. And we don't really have a good intuition for it. And vice versa. When the gauge theory is weakly coupled, the string theory is strongly coupled. This is, in fact, a precise implementation of an earlier idea that had been proposed by Tufte and Susskind, that quantum gravity should be holographic. In some sense, all the degrees of freedom of physics in some volume of space can be captured by a theory living on the boundary. This was originally motivated by considerations of black hole entropy, which I just told you is proportional to the area of a black hole and not the volume, as one normally expects. So Tufte and Susskind discussed this as a vague idea, and Maldacena made it precise with this formulation of gauge gravity duality. Now, what boundary conditions do we need to impose? The boundary condition that's required is that space-time approach a constant negatively curved space, something called anti-de Sitter space. So this metric is given here. It's just r squared times the metric of special relativity plus the r squared over r squared. This is a solution of Einstein's equation with negative cosmological constant. Now, as you all know, astronomers have discovered the universe is accelerating. This is due to, well, it's called dark energy, but it looks very much like it's a positive cosmological constant. So you might wonder why we're studying solutions of general relativity with negative cosmological constant. And the short answer is, if you want to study cosmology, you use general relativity with a positive cosmological constant. If you wanted to study anything else, you use general relativity with a negative cosmological constant. Anyway, this is what's needed for gauge gravity duality, and I'll try to argue that it's actually working. This metric has a interesting symmetry. You can rescale the radial direction by a constant a, and the tx directions by 1 over a, and the metric is clearly left invariant. So the gauge theory lives sort of at infinity. For large R, you can sort of rescale, if I take this out, and basically this is the metric on which the non-gravitational theory lives. And so this is giving an interpretation of this extra spatial direction, this holographic direction. And what it's telling us is that small radius corresponds to large distance, or low energy, in the gauge theory. Now, this gauge gravity duality has not yet been proven. It's still a conjecture, but by now there is overwhelming evidence that it's true. So we're going to assume it and see what its consequences are. Now, early on, after Maldacena first proposed this, there were two main applications that were studied. First of all, it was used to gain new insight into strongly coupled gauge theories. And in fact, it was shown early on that this provides a very simple geometric picture of quark confinement. Confinement is a complicated quantum field theory process, which is hard to describe in terms of QCD, but when you look at it from the gravity side, with this one extra dimension using general relativity, there was a very simple geometric description of quark confinement. Another application was that it was used to gain new insight into quantum gravity. In fact, it provided understanding of quantum properties of black holes. And let me just say a word about that. After Hawking's work, we were left with two fundamental questions. What is the origin of black hole entropy? After all, in all other areas of physics, entropy or thermodynamics is just an approximation to a more fundamental statistical description, and the entropy is a measure of the number of internal states, number of microstates. The fact that the black hole entropy is so large indicates that black holes must have an enormous number of quantum states, and we wanted to be able to describe them. And the second question was, does black hole evaporation lose information? If the black hole is irradiating, it'll eventually disappear. If it radiates a purely thermal spectrum, all the information about what was thrown in to make the black hole seems to be lost. And you don't have unitary evolution from your initial state to your final state. And Hawking argued for 3 decades that black hole evaporation would, in fact, violate quantum mechanics in the sense that it wouldn't be unitary. But gauge-gravity duality gave us answers to these questions. It was shown that the dual gauge theory, in fact, does have enough microstates to reproduce the entropy of black holes. And it was also shown, well, this sort of is immediate, that the formation and evaporation of a black hole can be mapped into a process in the dual field theory. But the dual field theory is an ordinary quantum mechanical system with an ordinary Hamiltonian evolution, and so it doesn't violate quantum mechanics. And after 30 years, Hawking finally conceded this point in 2004. Now, I was just talking about quantum mechanics and string theory, but in a certain limit, all these quantum effects are suppressed, and string theory does reduce to just ordinary general relativity with these unusual boundary conditions, these asymptotically anti-de Sitter boundary conditions. So for the rest of the talk, I'm going to be really just talking about general relativity. But in the last 5 years or so, there's been a new application of this gauge-gravity duality, and that is to condensed matter. In 2007, a few condensed matter effects, such as the Hall effect, were reproduced using general relativity. And there were various papers by these authors here. And the appealing thing of applying gauge-gravity duality to condensed matter is that the duality allows one to compute transport properties of strongly correlated systems at non-zero temperature. This is something which theoretical physics have very few other tools to do. So it was tempting to try to see what you get. Okay, so let me just say a few more words about the basic ingredients of this duality. A state of thermal equilibrium at temperature T. So you take any system you want, not gravitational, like a superconductor. Anyways, if you're in thermal equilibrium, you have a certain temperature T, and the gravitational description of that is a black hole with the Hawking temperature, the same Hawking temperature. So the black hole in the gravity gives you the temperature, describes the thermal equilibrium. Fields in space-time, coupled to gravity, are related to, or dual to, operators in the boundary quantum theory. And local properties of the gauge theory are related to the asymptotic behavior of these classical fields in the gravity solution. So that's just a little hint of the duality. But now for the rest of the talk, I'm going to concentrate on one application, and that is the superconductivity. Since I'm going to assume you're not all experts in superconductivity, let me start with a brief course. Just a couple of the key ideas. Okay, so in conventional superconductors like aluminum, niobium, and lead, pairs of electrons with opposite spin can bind to form a charged boson called a Cooper pair. And if you lower the temperature, there is a critical temperature, Tc, in which you have a second-order phase transition, and these bosons condense. The DC conductivity becomes infinite, and you have a superconductor. This is all well described by a theory proposed over 50 years ago by Bardeen, Cooper, and Schrieffer, called the BCS theory of superconductivity. In this theory, the electrons pair because of interaction with phonons, just the lattice vibrations, and this interaction is rather weak. So typically the Cooper pairs are rather big, in fact larger than the typical separation between the atoms in the lattice. Now, those are traditional superconductors, and their transition temperatures tend to be quite low. Starting in 1987, a new class of high-temperature superconductors, or 1986, high-temperature superconductivity was discovered, and these materials are called cuprates. They're things like yttrium, barium, copper oxide, and these materials are layered. You have copper-oxygen planes, and the superconductivity is associated with these two-dimensional planes. The highest Tc that's been found so far today at ordinary atmospheric pressure is a mercury barium copper oxide material, which goes superconducting at 134 degrees Kelvin. If you add pressure, you can raise this up to about 160 degrees Kelvin. So it's within a factor of 2 of room temperature. And of course, the idea of a room temperature superconductor is very exciting because of all of its possible applications. So this has attracted a lot of attention. In fact, just in 2008, a qualitatively new class of high-temperature superconductors were found. These are based on iron and not copper. They involve things like iron arsenic. But these so far have only gone superconducting at about 56 degrees Kelvin. Now, these materials are not understood. They've been studied intensively since '86, and even the basic pairing mechanism is not understood. What is known is that they're not weakly coupled, but there are sort of strong correlations, interactions among all the electrons in the material. So, because we have this duality, which allows us to relate some strongly coupled non-gravitational theory to ordinary general relativity, it's tempting to try to apply this to high-temperature superconductivity. So the first step is to construct a gravitational dual of a superconductor. And how do you do that? Well, this is work I did with Sean Hartnell and Chris Herzog back in 2008. Well, on the superconducting side, we need a notion of a temperature. And as I said, on the gravity side, that role is going to be played by a black hole. We also need a condensate, something which will turn on at low temperature and cause the system to become superconducting. And on the gravity side, we're going to model that by a charged scalar field. So the task now is to find a black hole that has scalar hair, non-zero scalar fields outside the horizon at low temperature, but no scalar field at high temperature. And this is not, at first sight, an easy task, because there are something called no-hair theorems. Right? Typically, if you put a scalar field outside a black hole, it wants to either radiate off to infinity or fall down the horizon. The only solution turns out to be the Kerr metric, the vacuum solution. It's hard to get matter just to want to sit outside a horizon. So at first sight, this doesn't seem very promising. But early in 2008, Steve Gupser came up with a very simple solution. He argued that a charged scalar field around a charged black hole would have this desired property. And the reason is easy to see. The Lagrangian for a charged scalar field is written here. There's sort of a kinetic term involving the coupling to the Maxwell field, the vector potential A, the charge Q of this scalar field, and a mass term. And you can see that if your black hole has an electric charge, so there's a time component to this vector potential, The effective mass of the scalar field is the mass you put into the Lagrangian, but there also gets a contribution from this coupling to the vector potential. But this last term is negative, because GTT is negative. And so this can produce an instability near the black hole, which causes the scalar field to turn on at low temperature. Now this seems like a simple model, and you might ask, why wasn't this noticed before? I don't really know, but one answer is that this doesn't work in asymptotically flat spacetimes. So if you have the usual boundary condition that we use when we study black holes, that it basically is an isolated system, and the space becomes flat asymptotically, you don't find any scalar field turning on. The scalar field will still radiate off to infinity. It turns out that these new boundary conditions are crucial. Having this space-time become asymptotically anti-de Sitter, approach this constant negatively curved space, is what keeps the scalar field non-zero outside the horizon. Now, at large radius, you can solve these equations, and the sort of electrostatic potential, this time component of the vector potential, goes to a constant mu minus another constant rho over r, and the scalar field goes to a constant psi, which I'll call psi 2, falling off like 1 over r squared. And gauge gravity duality relates these asymptotic constants to properties of the dual theory. So this leading constant mu is interpreted as a chemical potential, and this term rho is the charge density, and this term psi is, well, as I said, there's operators dual to fields in the gravity side, so there's an operator which I'll call O2, it turns out to have dimension 2, dual to psi, and the expectation value of that operator is given by this leading term in the fall off of the scalar field at infinity. So now you can go ahead and find the solutions. You just find the charged black holes in anti-de Sitter space, coupled to this charged scalar field, and then you can go out to large distance and read off what this condensate is doing from the asymptotic behavior of the scalar field. And here's the condensate as a function of temperature. And the first thing you note is that there is indeed a critical temperature above which the scalar field is just zero. The black hole just wants to be normal and not have any scalar pair, and so the condensate vanishes. Below a certain critical temperature, the ordinary charged black hole becomes unstable. It actually prefers to have scalar fields outside. The scalar field turns on, and if you look at the asymptotic behavior of the scalar field, you get a plot like this, where this condensate turns on rapidly and approaches a constant at low temperature. The critical temperature is set by the chemical potential. That's essentially the only scale in the problem, so that determines Tc. And this general behavior is very familiar in superconductivity. This is indeed what's seen in most superconductors, this rapid rise and then saturating at low temperature. It's predicted by BCS and is very, very common. I should mention that these hairy black holes with the scalar field have the property that as the temperature goes to zero, the horizon area goes to zero. And since the horizon area is proportional to the entropy, this is consistent with the idea that there's a unique ground state. You may know that the usual charged black holes, the Reiser-Nordstrom solution, doesn't have that property. At zero temperature, you still have a non-zero horizon area, indicating a large entropy and a very degenerate ground state. That seems sort of unstable in some sense from a condensed matter standpoint. And here we're seeing that, in fact, the area goes to zero in this superconducting, well, in this case. So this is what the black hole is doing. But what we really want to do is calculate the conductivity to check if it's really acting like a superconductor. So to calculate the conductivity, we use linear response, and that means we have to perturb the black hole. We perturb the black hole with something which has harmonic time dependence, e to the minus I omega t, and we require that the perturbations have ingoing wave boundary conditions at the horizon. That's physically what you expect. Waves go into the black hole, nothing comes out, and that indeed is what you need to get sort of ordinary retarded propagation in the dual theory. We're putting in a frequency omega, and we're going to calculate the conductivity as a function of omega, sometimes called the optical conductivity. So how do we do that? Well, we have now perturbed the Maxwell field, so there's a linearized Maxwell field which has an x component. The background just has the time component. And this perturbation asymptotically, again, has a leading term, a 0, a subleading term going like 1 over r. The gauge gravity duality dictionary says that this leading term is essentially a vector potential in the dual theory. We're assuming homogeneity, so there's no spatial dependence, but it's oscillating in time, so there's an electric field proportional to the time derivative of that. It just gives I omega times A naught. And the duality says that this subleading term is in fact the induced current. So more generally, the leading term is usually a source, and the subleading term is a response. So in this case, we apply an electric field, we get an induced current, and you read this off from the solution. And then the conductivity follows from Ohm's law. J equals sigma E. So sigma is just J over E, or from this dictionary, it's 1 over I omega times the ratio of the first subleading term in this perturbation over the leading term. So now you can just solve for the perturbations of the black hole. Look at this ratio and see what you get. And here is the conductivity at low temperature. So this is, the conductivity is complex, so this is just the real part of the conductivity. And what you see is a gap at low frequency, and then the rise up at higher frequency. This is indeed a very common feature of superconductors. There's an energy gap above the ground state, and you need a certain amount of energy to excite particles, so that's familiar. And the important thing is that there's this delta function right here at 0 frequency, which is the infinite DC conductivity telling you that this is really a superconductor. Okay, so this is indeed acting just like an ordinary superconductor. And so once we saw this, we got more ambitious and said, well, can we do other things? And of course, the thing that people often do with superconductors is to construct something called the Josephson junction. A Josephson junction consists of two superconductors separated by a weak link. And there's different kinds of Josephson junctions, depending upon the nature of that link. If you have an insulator between two superconductors, you get something called an SIS junction. If you have a normal conductor, you get an SNS junction. And if you just have a narrow superconducting bridge, you can get this Josephson junction as well. Now, Josephson predicted early in the 1960s that even without any voltage difference across your junction, you will have a current. And the current will take this form of a maximum current times the sine of an angle gamma, where gamma is just the phase difference between the condensates in the two superconductors. So remember, the condensate is a complex function. It has a phase as well as a magnitude. In the previous example, the phase was constant everywhere, so I didn't mention it. We could just set it equal to 0. But when you have two superconductors, you can choose a relative phase between them. And Josephson said that if you do that, you will get a current. So I'm now going to show you how to construct an SNS junction using general relativity. This is work I did with a postdoc, George Santos, and my student Benson Wei just a couple years ago. And the key idea is to remember that in the example that I showed you before, the critical temperature was set by the chemical potential. So if you have a chemical potential which is a function of x, and suppose it's sort of constant most of the time and equal to this mu infinity, but then in a little gap it dips down to some lower value mu naught. Then there's a range of temperatures, sort of indicated here, such that you're below the critical temperature most of the time. In other words, you're in a superconducting phase most of the time, but in this gap region, you're actually above the local critical temperature, and so this will not be superconducting. This will act more like a normal conductor. And for this system, the whole critical temperature, when you lower the temperature, is still set by this asymptotic value, constant value of mu. So you go ahead and you solve. This is now solving for general relativity coupled to a Maxwell field and the charge scalar with the boundary condition that you want your time component of the vector potential to have this funny shape at infinity. And so here are the results. So here is your electrostatic potential as a function of x, one of the spatial directions, and z. Z is the radial direction into the bulk. It's convenient just to repackage r in terms of a coordinate that goes from 0 to 1. So z equals 1 at infinity back here, and you see the input. This is the boundary condition mu of x having that shape, and this is the behavior of a of t as you come into the bulk, and the z coordinate vanishes at the horizon of the black hole, and that's down here. So this is a sub t plotted in the vertical axis, x over here, and the radial direction going back. So this is what this electrostatic potential looks like. The scalar field, this is just the magnitude of the scalar field, is plotted here. Off at infinity, it goes to 0. That's the 1 over r squared fall off that I said that it has at infinity. But at the horizon, it's not 0. Away from the gap, it's turning on pretty uniformly. This is what it did before in the homogeneous case. Inside the gap, it's heavily suppressed. Not strictly 0, but it's heavily suppressed. Okay, so this is what some of these solutions look like. But again, what we want is this to check this relation predicted by Josephson. So in these cases, we can put on a current and measure the phase difference. Turns out to be easier to do it that way than putting in the phase difference and checking the current. But nevertheless, you can plot. This is now the current as a function of the phase difference across the two superconductors. The red dots are what we get from general relativity. And you see the black line is a sine curve. And you see that they are following extremely well the predicted Josephson effect. That the current is indeed given by some maximum current times the sine of the phase difference between the two superconductors. You can also check how this maximum current depends on the width of the junction. So here's the maximum current as a function of the width of the junction. The red dots are the data, and this solid line, which goes through all the points, is a fit to a simple exponential fall off. It goes like e to the minus L over some coherence length, c. And this is just what you'd expect. From Josephson analysis, these Cooper pairs are basically tunneling through this gap, and so you expect an exponential dependence on the width of the gap. In general relativity, we're just solving the classical field equations, but nevertheless, we find exactly the same exponential dependence. This little insert here is talking about how the behavior, how the condensate itself behaves inside the gap as a function of the width. That also falls off exponentially. There's a theoretical prediction that it should fall off like, L over 2c, where that's the same length scale, and indeed we find that to be the case. So far I've shown you that we are reproducing standard qualitative features of superconductors, the superconducting phase transition, the behavior of Josephson junctions. But now you can try to get even more ambitious. You can ask, can one do more than reproduce qualitative features of condensed matter systems? Can gauge gravity duality provide a quantitative explanation of mysterious properties of real materials? And in the last 15 minutes of my talk, I'm going to try to argue that the answer is yes. To have any hope of doing this, we have to make our models a little more realistic. And the main thing that's been left out so far is the lattice. All of our discussions, well, Josephson junction had a little dip in it, but before that we were dealing with sort of uniform or homogeneous solutions of general relativity. But of course, condensed matter systems are not like that. So in work last year with George Santos and David Tong, we put a lattice into these gravitational models. And the first thing we did is not to worry about superconductivity. Let's just look at an ordinary conductor with a lattice. So that means in the bulk, in the gravity side, we only have general relativity coupled to a standard Maxwell theory. It's almost as simple as it can get, but we have these unusual boundary conditions. We introduce the lattice by making the chemical potential be a periodic function of x. So now we're going to require that the chemical potential not have one little dip in it, but actually oscillate with some wave number k naught and some amplitude a naught. Before I tell you what we get from the gravity side, I'll just remind you of a very simple model of a conductor. So we have some idea of what we're maybe going to see. The simplest model of a conductor is the following. We suppose that the electrons in a metal satisfy an equation like this. It's just the mass times the acceleration is the force due to the applied electric field minus mv over tau, where tau is a relaxation time, and this last term is just modeling some dissipation. And then you can argue that if there are n electrons per unit volume, the current density is just n times the charge E times the velocity v. If you apply an oscillating electric field, e to the minus I omega t, you can solve this equation for v, compute the current J, and then using J equals sigma E, compute the conductivity. And what you find is this formula, where the conductivity is a function of omega. It goes like a constant k times this relaxation times tau, divided by 1 minus I omega tau, where k is essentially the number density of electrons times E squared over m. And this is called the Drude model, a conductor first proposed in the early parts of the 20th century. So you notice that if you take tau to go to infinity, if the relaxation time becomes very long, the imaginary part of the conductivity just has a simple pole, goes like 1 over I omega, and the real part would go to, you can show that the real part goes to 0 if omega is not 0, and it diverges if omega is 0. In other words, it goes to a delta function. So, first of all, I'll just remind you what the optical conductivity looks like in a material without the lattice. So if we do the calculation on the gravity side and perturb it without any charge scalar fields, nothing, we get these type of behaviors. The real part of the conductivity as a function of frequency is on the left, the imaginary part as a function of frequency on the right. And the unfortunate thing is that there is still a delta function right here at omega equal to 0, indicating an infinite DC conductivity. Now this has nothing to do with superconductivity. It's an artifact of translation invariance. This delta function here is, it's correlated with this pole in the imaginary part of the conductivity. But it's there because of momentum conservation. In a translationally invariant system, momentum is conserved. The charge carriers can't dissipate their momentum, and so when you apply an electric field, they just accelerate. And that means that you have infinite conductivity. So that's an awkward feature of the model without a lattice. So we put the lattice in, and that delta function goes away. It gets resolved. And what we find when we do the calculation with our more realistic model is the real part of the conductivity now starts to rise and approaches a finite limit at omega equal to 0. There's no infinite, the finite conductivity. And the imaginary part rises as it did before, but rather than having a pole, it turns around and comes back down. So what I want to do now is to zoom in to this low frequency behavior of the conductivity and see what we get. At low frequency, the conductivity computed from gravity by perturbing these charged black holes is exactly given by this Drude formula. So there's the Drude formula again. This is the real part of the conductivity as a function of frequency. The imaginary part is a function of frequency. And you see these lines are just fits to this Drude form. It looks like a 2-parameter fit, works very well. But in fact, it's a 1-parameter fit, because this constant k, I said, is related to sort of the density of electrons in our dual system. And if you take a translationally invariant system, then you have infinite relaxation time. This goes just to a simple pole. And in fact, if you take the k that you get from the translationally invariant case, that's the coefficient of this pole, you get exactly the same k as here with the lattice. So k is in fact fixed, and you're fitting all the data to just tau. We've changed the parameters of our model. We've changed the lattice spacing, the lattice amplitude, the temperature. In all cases, we find this simple Drude behavior coming out at low frequency. I mean, it seems remarkable that general relativity should know anything about this Drude formula, which was originally proposed by talking about charged particles and interacting with some electric field and some dissipation. Our gravity theory only has Maxwell fields and gravity, but it's coming out, and it's very robust. But what's even more remarkable is what happens at slightly higher frequency. At slightly higher frequency, at this intermediate frequency, we find a power law, a certain scaling. The absolute value of the conductivity goes like a constant b over omega to the 2/3 plus a constant offset c. So here is the absolute value of the conductivity as a function of frequency, and here's the phase. The phase is approximately constant over this range. And this power law, this exponent 2/3, is again remarkably robust. We've changed the lattice spacing, the temperature, and it doesn't change. It's always 2/3. To make that more clear, let me show you a log-log plot where we subtract this constant offset from the absolute value of the conductivity as a function of frequency. These curves are 4 different temperatures in some range here. And what you see is that the curves are all parallel. Well, first of all, they're straight lines. This is the Drude region. It's very low frequency is the Drude peak. In this intermediate frequency region, they're straight lines indicating a power law. The lines for different temperatures are certainly parallel, so the exponent is the same, the 2/3 is the same. But in fact, they're not only parallel, they're lying right on top of each other, which tells us that this coefficient b is temperature independent. Okay, so that comes out of general relativity, and you can ask, well, have we ever seen something like this before? This is not what's predicted by standard theory. The Drude model, if you look at what happens at high frequency, the absolute value of the conductivity falls off like 1 over omega. There's something else called a Fermi liquid theory, which predicts a 1 over omega squared. So it's not common to see this 1 over omega to the 2/3. But then you look at the cuprates. And now this is real data taken on a particular cuprate of bismuth, strontium, calcium, something material, commonly called visco. Data taken in 2003 by Van der Merle. He plots the absolute value of the conductivity as a function of frequency for various temperatures, and these are all above the superconducting transition. This material has a superconducting transition temperature of about 90 degrees. So he's looking at the normal phase, and we were looking at sort of just normal conductors. And what he finds is very similar to what we see. There's a Drude behavior at low frequency, a power law, this is a log-log plot, a power law behavior at intermediate frequencies, and you ask what is the power he sees, and indeed, it's omega, essentially omega to the minus 2/3. This is viewed as a big mystery in the condensed matter community. Nobody really understands why this is coming out of this material, and what we find is that it actually is predicted by general relativity. I can't really tell you why this is working. I mean, this seems miraculous, but it's what we get. So, having seen that, this was above the transition temperature. You can ask what happens if you go below the transition temperature. So, that's what we did just earlier this year. We put the superconductor back in to our model with a lattice. We added the charge scalar field. So now we have to study sort of the charge scalar field in the gravity theory with this lattice boundary condition. And what we find is, first of all, there is still a superconductor. The delta function, which was there in the superconducting regime, does not get broadened, does not get spread out when you add the lattice. That's good. We still have an infinite conductivity in the superconducting regime. But there is, in addition to the superconducting component, a normal component to the conductivity. which is acting very much like the sort of conductivity that we've seen above Tc. And when we look at the intermediate frequency region, so we again find that this normal component has the Drude behavior at low frequency and a power law behavior at intermediate frequencies. And in fact, it's the same power law. It's the same b over omega to the 2/3 plus a constant c. These are four different absolute value of the conductivity minus the offset as a function of frequency, four different temperatures, now all below Tc. T over Tc of 1, 0.97, 86.7. This curve 1 is the blue one. So that's what I was showing you before. That's really the system without any condensate. And these other curves are below Tc, and they're lying right on top of each other. The coefficient b and the exponent are totally unaffected by the superconducting phase transition. So what's seen in real materials? This is now 8 plots showing 8 different samples of this material visco, which differ in something called the doping. Right? They replace a certain fraction of the atoms with some other atom to increase sort of the number of free electrons. In each plot, there's the absolute value of the conductivity as a function of frequency. These are log-log plots. Let's just look at one of them, because they all look very similar. In one of them, okay, so I should say what's the label here is giving you, these are some, well, UD is underdoped, and the next two numbers are the critical temperature. So this material goes superconducting at 67 degrees Kelvin, then you increase the doping, and the critical temperature goes up to 96, that's optimally doped, and then these are overdoped, and the critical temperature goes down again, all the way down to 60. Okay, but they're log-log plots, and they show this power law, which has the slope, omega to the minus 2/3. But the important thing is if you look at the temperatures, I don't know if you can see that, but they now go from above Tc to 295 all the way down to below Tc, 29. In each case, they've plotted now the conductivity both above Tc and below Tc. They see absolutely no change, exactly like we see in general relativity. Now, I have to say there are some differences, right? This is not working perfectly. The main difference is we have this constant offset, right? We model this to a power law plus a constant offset. There's apparently no offset in the cuprates. When they plot their data, they just plot in the absolute value of the conductivity. There are also differences in exactly sort of what range of frequencies that they see the power law in. But in both cases, it's not very high frequencies or very low frequencies. It's some intermediate frequency region. Okay, so I'm out of time, so let me summarize. I've tried to argue that in addition to describing gravity, gauge gravity duality predicts that general relativity can describe non-gravitational physics. And I've given evidence that general relativity can indeed describe superconducting phase transitions, Josephson junctions, and anomalous power laws seen in the optical conductivity of cuprates. Thank you.